Hello, everyone, and welcome to another wonderful day of chemistry. So today, we're going to go ahead and get a little basic. Let's talk about hydroxide and bases. So far, what we've mostly been using is our weak acids and ice tables to determine the pH of a solution. However, we can take this same idea and flip it on its head and use ice tables to figure out the pH of a weak base solution when it's placed in water. Because if I add an acid, the pH should go down as I release more protons. As I add a base, the pH should go up as I'm chewing them up and taking them out. So let's go ahead and try and determine the pH of one of those quintessential weak bases, ammonia. So let's say I put 0.1 molar solution of ammonia in water. So this would be fairly synonymous with a nice weak cleaner like a very diluted Windex. So in this case, that ammonia can react with the water, pull up some extra protons to make ammonium and hydroxide. Now, the issue is you might not be able to find a good equilibrium constant for this reaction. You may actually be required to look up the pKa of ammonium. So ammonium actually has a pKa of about 9.25. Well, I'm interested in the base reaction, so let's go ahead and find that pKb, which would just be 14 minus the pKa. Turns out ammonia has a pKa or pKb of about 4.75. So using this, we can go ahead and find the actual Kb value just by raising that pKb to 10 to the negative power. So turns out we've got a Kb a little bit less than 10, or a little bit greater than 10 to the negative fifth. And the actual reaction it corresponds to will be the hydroxide times the ammonium divided by the ammonia. So again, watch out for that tricky nomenclature, ammonium, ammonia. So using this, we can go ahead and set up our ice table. So again, we're going to ignore water, and we're going to be producing hydroxide and ammonium, and we're going to start with about 0.1 molar ammonia. Again, it's just like we did with protons, assuming no hydroxide or ammonium present in solution. Then we're going to consume the ammonia and end up producing our hydroxide. So again, our equilibrium will be very similar to what we saw before. We'll have 0.1 minus X of the ammonia and produce equal amounts of ammonium and hydroxide. We can then go ahead and shove this into our Kb equation. And so, like most of our equilibrium constant equations, it turns out to be quadratic. Drat. However, let's go ahead and see if we can make an approximation. Is my x going to be fairly small? If it is, we can go ahead and drop out this minus x, and it turns out that x squared will then be equal to 0.1 times our Kb. So this means that we can get our hydroxide and ammonium concentrations both by solving for x. So that should be equal to the square root of our initial base concentration times the Kb, or about 1.33 times 10 to the negative third molar, or 1.3 micromolar. So yeah, 0.1 minus this, we're actually fairly good. It's about a 1% deviation, or a 1% ionization. And let's go ahead and confirm this. So now that we've got our OH and our ammonium concentration, let's go ahead and try and figure out both our pH and our percent ionization. So to get the pH, let's go ahead and start by solving for the pOH. So using this, we can find negative log of OH ends up being about 3.88, so just under 4. Then we can convert this to pH by doing 14 minus the pOH, and ta-da! The pH of the solution will be just over 10. So it'll actually be a fairly basic solution. So this is barely on the edge of what's considered livable. The most basic alkaline lakes you'll find out there hit a pH of about 10. Now let's go ahead and take a look at the percent ionization. So for this, we'll go ahead and divide. Now instead of our amount of conjugate base over acid, it's the amount of conjugate acid over the initial amount of base. So it turns out with a degree of ionization of 0.0133, or about a 1.3% ionization. So this means that our assumption of x is of x being small is fairly sufficient, though a very substantial amount of our ammonia did break apart. And this can play a role as ammonia and ammonium will have very different properties. Turns out ammonia can actually degas. It's naturally a gas phase species. Ammonium, not so much. It tends to be fairly locked in solution. And so we're starting to see some really interesting multi-reaction dynamics. And we'll go ahead and look into that a little bit more next time as we talk about polyprotic acids. What happens if an acid can donate more than one proton? Until then, take care.